What if everything we know about space and time were an illusion? Imagine yourself on a boat in the middle of a vast ocean, surrounded by an infinity that completely envelops you. There are no boundaries, no horizon, only immensity. Around you, waves rise and fall, but these waves are not made of water. They are the very fabric of reality, bending and distorting. This is the image Albert Einstein used to describe the concept of space-time. But what does it really mean? And why did it forever change the way we understand the universe? At the start of the 20th century, Albert Einstein was a young man with ideas so revolutionary that he was not yet recognized as the genius he would become. He was not a mythical figure, but a simple clerk at the Swiss patent office in Bern. Every day for 8 hours, he dealt with bureaucratic work. But when the workday ended, his mind focused on the great mysteries of the universe. In 1905, remembered today as his Annus Mirabilis, Einstein proposed an idea that would forever change science. Space and time were not two separate entities, but two sides of the same coin. This concept, called space-time, not only shed new light on the nature of reality, but also opened a new chapter in scientific thought. Before Einstein, scientists thought of space as a rigid, immutable box in which objects moved as if trapped, and of time as a river flowing uniformly and independently of anything happening in the world. But Einstein, with his innovative vision, suggested that space and time were not independent entities, but a single interconnected reality that responded to the forces of the universe. This concept was so startling that many of his contemporaries struggled to understand it. But Einstein didn't stop at the theory of special relativity, which described the behavior of moving objects. Over the next 10 years, he worked tirelessly to develop a theory that also included gravity, a phenomenon Newton had described with mathematical precision, but without explaining its origin. In 1915, Einstein presented his theory of general relativity, a work that not only explained gravity as the curvature of space-time, but also opened new doors to understanding the universe itself. To better grasp this, imagine placing a heavy ball on a trampoline. The trampoline bends under the ball's weight, creating a dip. Now, imagine rolling a smaller ball along the trampoline. It won't follow a straight line, but will move along the curve created by the weight of the heavy ball. Similarly, planets and stars do not move through space as if it were an immutable void, but follow the curves created by the mass and energy in their surroundings. How can we be sure this theory is correct? One of the first decisive proofs came in 1910 during a solar eclipse. British astronomer Sir Arthur Eddington, conducting observations on the position of stars during the eclipse, noticed something extraordinary. The light from stars near the sun's edge did not behave as expected. The light appeared bent, exactly as Einstein had predicted. This phenomenon, known as gravitational lensing, demonstrated that space-time could be curved by mass. Gravitational lensing is one of the most fascinating effects of general relativity. Imagine observing a distant galaxy through a giant lens made of distorted space-time, capable of bending and amplifying the image of faraway objects. A striking example of this phenomenon is the Einstein cross, a quasar located 11 billion light-years away that appears as a cross-like illumination of distant galaxies, produced by the distortion of light by a massive object in between. Beyond explaining gravity, general relativity has had a direct impact on our daily lives. For instance, GPS systems we use for modern navigation rely on Einstein's theory. Satellites orbiting Earth must account for time dilation, an effect predicted by relativity, as time flows faster for them than it does on Earth's surface. But Einstein's insights are not limited to everyday phenomena. He also predicted the existence of black holes, those mysterious regions of space where gravity is so intense that nothing, not even light, can escape. For years, black holes were considered purely theoretical, but in 2019, scientists managed to capture the first direct image of a black hole located in the M87 galaxy. The photo, showing a luminous ring surrounding a dark shadow, strikingly confirmed the predictions of general relativity. Black holes are now regarded as some of the most extreme laboratories for testing the limits of relativity. When an object approaches a black hole, it experiences such intense gravitational forces that it gets stretched and deformed in a process known as spaghettification. At the center of a black hole lies a singularity, a point where the curvature of space-time becomes infinite, a mystery scientists are still striving to understand. Despite its extraordinary successes, general relativity cannot explain everything. When entering the realm of subatomic particles like electrons and quarks, space-time seems to behave in ways that elude our understanding. In fact, relativity is not compatible with quantum mechanics, which describes the behavior of fundamental particles. Scientists are searching for a unified theory that can combine general relativity with quantum mechanics, the so-called quantum gravity theory. One key to achieving this goal may lie in the study of gravitational waves, ripples in space-time caused by extremely violent cosmic events, like the collision of two black holes. Gravitational waves were first detected in 2015, once again confirming Einstein's predictions and opening a new window onto the universe. These waves are not just a scientific curiosity, but allow us to listen to the universe in an entirely new way, revealing events that cannot be observed with traditional telescopes, such as the merging of black holes or neutron stars. Each new discovery in the study of space-time raises new questions. How does space-time behave near the singularity of a black hole? What happens when gravity and quantum physics are combined? And what will the future of cosmic exploration hold? The answers to these questions could once again rewrite the laws of physics. When you look at the starry sky, remember that you are observing the fabric of space-time, a tapestry of gravity, light, and motion that connects everything in the universe. It is a never-ending story, an infinite dance of energy and matter that reminds us of how vast and mysterious the cosmos truly is. Thank you for exploring the mysteries of the universe with us. Leave a like, subscribe to the channel, and activate the notification bell so you don't miss our next videos.